Okay. Well, get this gross hair out of my mouth and let's dive in. So I'm just gonna open up Alex over here real quick just to make sure my dates are right and I don't have anything off. Oh no, by all means, take forever, computer. That would be great. What homeworks are due tonight? Let's see. So, how about now? Because Andrew, I actually had it built into the log, into the speaker here, which doesn't actually have a microphone. How's it? Is it better now? Because I'm okay, good. Good. I wanted to improve it. We've got that alarm is still right outside my door, and they still haven't fixed it. So it is it's still beeping for no reason, and this won't pick it up as much as the mic on the computer will. So that was my reasoning. And I think the audio sounds better up here. So tonight you have the 1-6, which we have already done, and then 1-7 and 1-8 are right now due on the 20th. I would not be surprised if 1.8 gets pushed to the 24th, but we'll see. Just so you have the weekend to do it. But let's see how today goes first, and then I'll reopen this. Let's just go ahead and do this. Chapter 1 review should probably be open. You notice that the assignments get put in the order that their due dates are. If you ever notice me doing something, 2-1 and 2, oh, ignore that. We haven't even touched that yet. Ignore that. I'm actually going to turn it off so it doesn't freak anybody out. Yeah, so we'll ignore those. Yeah, and then we'll get the calendar right once we get this test out of the way. All right. So, but yeah, so you'll see that the due dates, this is lined up by due date. So sometimes if things don't line up the way I want to, you may see me set something due at 11:58 and then the review at 11:59. That is just there because this is the only order that it will show up in. So if you ever see something weird like that, why is it 11:58 or 11:57? It's because I'm trying to make these appear in the correct order. But no questions if there are none. Oh, we'll be taking the principal blank notes. Oh, yes. Yes, I will, Tenny. The printable blank notes. Oh, no, they are. They're up. Yeah, the 1718. And then once we get, I just haven't converted them over to PDF for chapter 2 yet, but they're ready. So yes, I will submit those. And got a really good, I've been writing down everything. Let me make sure. Chapter 2 due dates. 171. And then Stephen asked about lockdown browsers. I think there's only 2 people that are having trouble right now. Everybody else was able to either do the original or was able to do the modified one that we had. But I'm going to check in. Oh, and I'll check in just on the list of who needs what. But for the next 48 hours, my goal is I think everybody in here needs a midterm grade posted. So that is my goal right now, is to make sure that you have a midterm grade posted. You'll notice in Blackboard, if you jump into the grade book or the grade center, you're going to start to see all the Alex assignments show up. We've finally gotten those to talk to each other. So post notes for 161718. So yeah, you'll notice those grades, they're still updating, so it may just look like it's a bunch of blanks right now, but it will update and you'll be able to see your grade. So yes, Andrew, link to the extension, I will. Okay, thank you. Yes, so just the ones for chapter 2. Yes, I will. I'll have those. And what I'm going to do is probably once I just convert them all to PDF, I will just put everything in that folder. I think everybody will be okay. Post blanks for future notes. All right. And Andrew needs the extension. Okay, email. Anybody else while I've got a captive audience? For lockdown browser. Anyone else know that their computer isn't working or doing what you want it to? Okay, expect an email later this week with that same question. If I look online and you were not able to do the original practice test or the modified test, I'm going to be getting in touch with you to work out some way that we can proctor your exam and make sure everybody's takes the same test. All right. So with that said, 1.7 you're going to notice is just a little out of order. Quite literally page 2, and you saw me move some stuff around last time. I have moved the piecewise function over to the part 2. So if this looks funny or weird or out of order, it was just the way that the pages came over. So last thing we did, we talked about increasing, decreasing, and constant. Now, I did not get to talk about this picture, and I kind of want to really quick. So here is the deal. Let me show you, okay, for all this fancy math stuff that we do. Remember we talked about when is a function increasing, right? And in this case, I is an interval that is contained within the domain of the function. So an interval, right? So interval, we've run into this before. We've run into interval notation, right? So like -2 to 3 is an interval, and it would be super great if you put the x as an element of to indicate it, because if you don't, it looks like it could be an ordered pair as well. So notation is starting to become important. But so for us, what we would do is name I as some interval. And this definition says that f is increasing on the interval I if f of x sub 1 is less than f of x sub 2 for all x1s and x2s on the interval I. So here's x1, here's x2, and this has been labeled as the interval. The interval starting with this x value ending over here. Typically intervals are open, meaning they don't include endpoints. And the idea is that the definition f of x is increasing if on some interval I, f of x sub 1 is less than f of x sub 2. Well, here's x sub 1, here's x sub 2. I come up to the function, and what I get out, my output, is f of x sub 1. X sub 2 is over here. I got f of x sub 2. Now, it's not enough for it just to happen in one place, because I could be, down, up in the middle of that, but we've got this on an interval. So it means for every x values in this interval, if I have x sub 1 is less than x sub 2, just meaning x sub 1 is to the left of x sub 2, then every time you pick 2 points, it better be the point that's to the right has a higher output than the point to the left. So if I put x1 here and x2 here, do we still have that? Yeah, because there are the points on the function, and x sub 2 corresponds to a higher value than x sub 1. What about if I do them here and here? It still holds, right? So it's across that entire interval that it's increasing. All right, What about decreasing? It's the exact same concept, but the other way. It's decreasing if my leftmost point, or my left point to the left, has a higher value or output value than the rightmost point. So I'm decreasing if I'm falling from left to right, increasing if I'm rising from left to right, and then constant on an interval if for every value in there, what I plug in for x sub 1 and what I plug in for x sub 2 return the same value. Now, if the function did anything like this, where it changed behaviors and then it came back, this interval is no longer good for us, right? Because based on this function, my interval or my function is not constant on this entire interval. What do I do in that case? Well, in that case, I would need to shrink the interval. I am constant from here to here, right? And put x1 here and x2 here. And I still meet the definition, right? F of x sub 1 is there, f of x sub 2 is there, and they are the same, right? So whenever you see one of these, what I want you to understand is these pictures that you're looking at, imagine these are really, really zoomed in tight. Because if they function up and down, what I'm talking about is the function is rising on some interval, meaning it's just from left to right, there's a function and it's rising over that entire interval. The interval doesn't have to be particularly big. But it just needs to have this same behavior from just to the right of the endpoint all the way over to the last point in the interval. So this is the definition of that. Okay? Now, does that mean anything to you mathematically? Probably not. It's more of it's a conceptual thing, but I do want you to start thinking in those terms. We've already been introduced to intervals a couple times, so we want to talk about them formally. All right. Now, other thing we talked about was symmetry. And I mentioned that there are two types of symmetry that we would run into when we were really dealing with functions. And that is symmetry about the y-axis and symmetry about the origin. If I have symmetry about the y-axis, then I've got about the y-axis. That means the point, if the point xy is on there, is on the graph or part of the function. So if xy is on there, then negative x, y is on there, right? So xy is here, negative xy is right there. They're both on the function, all right? So this is symmetry about the y-axis. The other way to do this was symmetry about the origin. And the rule says if you have the function, or if you have the point xy, then you also contain the point negative x, negative y, right? So the symmetry about the origin is the one where you rotate. So in this one I have, this is about the y-axis. Yes. This one's about the origin. So meaning if I stopped, let me see if I can force this, because I kind of want to see it. It doesn't have the rotation. Oh, well. Well, if I take this, so what I want you to do is everybody turn your head all the way around. And so like this, if I turn my head and I stand on it for just a half a second there, that function, looking at number 2, looks exactly the same as if I was looking at it upright. So looking at it upright and then looking at it upside down, it starts on the left, it goes down, and then it comes up. When I flip my head back over, it starts on the left, it goes down and comes up. So that is symmetry about the origin. About the origin. Now, the third one, let's go ahead and put the caveat in here. This is not a function. Why not? What rule does this break? Ideas? Why is that green line not allowed to be a function? Exactly, Stephen. It does not pass the vertical line test, right? If I plug in, this is 0, it looks like each dash is worth 1 unit. So if I plug in 2, this graph returns both. That's a positive 2 up there and pretty much a negative 2 down here. That's the definition of a function. It can't do that, right? You're not allowed to. Ugh. Oh my gosh, was that a straight line, Larry? Come on, man. So if I start here and I come down, I hit the curve twice. And that means what? When I plug in 2, what do I get? I don't know. I get 2 different answers. I don't know which one of them is right. So that means this is not a function. Unique inputs, all unique inputs do not lead to a unique output. However, it still has symmetry though. And it's the only way that you're ever going to see this symmetry is with a graph that's not a function. Okay, where is its symmetry? Well, this has symmetry about the x-axis. All right. So if you get it, when you get in here and you start looking at the questions, remember the 2 types of symmetry you're going to see with functions are symmetry about the y-axis and symmetry about the origin. The only other type of symmetry that we talk about is symmetry about the x-axis. That's never going to appear unless the graph you have is not a function. Okay? There's one shape that can have all of these. Okay? Anybody want to guess what it is? What can have symmetry about the x-axis, the y-axis, and the origin? Think about that. Okay? It's not so much a problem that I want you solving, just something fun to think about. Now, how about this graph? All right. Well, here we go. There's the rotate. Okay, so that went around the y-axis. Did I have the same function when I started it flop over on itself? No, this looked different, right? Starting here, coming down, hits the y-axis, comes up, has a skew point where it changes its behavior, and then takes off. So if I take these and do that, watch number 1 when I rotate, when I go horizontal. It's going to come out over here, but see, that shape is exactly the same, right? It would honestly just be better to just undo there. All right, so this one doesn't have symmetry about the y-axis. Does it have symmetry about the origin? No, because if I take this and I rotate it 180 degrees, this little dip right here is going to come up above the x-axis, and then everything else is going to be below. So this has no symmetry, at least the way we define it. No symmetry. All right. That is a word that will always look misspelled to me. All right. So how do we feel? Symmetry good. I can have symmetry about the x-axis, the y-axis, and the origin. But if I'm dealing with functions, I'll only talk about symmetry about the y-axis and symmetry about the origin. All right. So we're going to add another feature, and that is functions that are even and functions that are odd. All right. So the definition of even and odd functions is up there again. And I'm going to kind of reduce it down to the algebra that it states. All right. So if a function is even, then I get two things. First of all, if I plug in negative x into my function, I will get back f of x. All right. The other feature of this is I will be symmetric about the y-axis. If a function is odd, when I plug in f at negative x, I get back negative f of x. So in this one, if I plug in -1, so let's say I have f at 1. If I plug in -1, I should get back the exact same thing I got when I plugged in 1. Here, if I plug in negative something, when I get done, that negative migrates to the outside. And what that does essentially is it really just, think about if I take a negative and put it out in front of a function. What does that do? You just distribute the negative. It changes the sign of every, of all the terms. So if I'm odd, this is the relationship I have algebraically. Graphically, this is going to look like, or this is going to be symmetry about the origin. All right. So with that in mind, and the next page is just the original 8 basic graphs. We're going to look at these and try to determine which is even, which is odd, which is neither. All right. So never get these quite the right size for everybody to see. There we go. So let's start with something easy. Let's see if we can see one that's definitely even or definitely odd. Let's ignore linear for a second, and let's jump right here. F of x is x squared. That's a parabola. Okay. Do I have symmetry about the y-axis? Meaning, if I take that as like a book page and I flip it over on to the left side, right across that y-axis, let that be the spine, the graph part on the left, on the right, lands directly on top of what's on the left already. Does that work? Yeah. Do I have this property that f at negative x is equal to f at x? Well, let's look. When f is 1, or excuse me, when x is 1, f of x is 1. When x is 2, f of x is 4. What happens when I do -1? I get back 1. What happens when I plug in -2? I get back 4. Yeah, those match, right? These are the same. These are the same. So this is an even function. All right. How about the cubic? The cubic does not have symmetry about the y-axis. Okay. But if I rotate the graph about the origin, I do have that symmetry. Does it meet the mathematical statement? If I plug in negative x to my function, I end up with negative f of x. So when x is 1, f of x is 1. When x is 2, f of x is 8. Well, now when I plug in -1, I don't want to get back 1. I want to get back the opposite of this, which is -1. Does it? Yeah, right? Plug in negative x, y becomes negative. Plug in negative x, y becomes negative. Did it match? Yeah, it did. Right? So this is an odd function. All right. Let's keep looking. Square root function. Okay. Well, you can't be symmetric about the y-axis or about the origin if your function doesn't exist to the left of the y-axis or to the left of the origin. Right? I cannot be symmetric because there's nothing on this side to land on top of. So square root has no symmetry. Cubed root, however, if I rotate this 180 degrees, don't I just end up with what I started with? How about our f at negative x is equal to negative f at x? Does this work? When I plug in 1, I get 1. When I plug in -1, do I get -1? Yep. When I plug in 8, I get 2. When I plug in -8, do I get 2? Yes. So I have symmetry about the origin. I match up here. So this is an odd function. All right. Let's keep looking at the traits here. Absolute value. Yeah. This is an even function. Think about it. It's probably the most, by definition, the even function. Because remember the definition. If I plug in -x, do I get back what I originally put in? Yeah. If I plug in 1, I get 1. If I plug in 2, I get 2. If I plug in -1 to the absolute value, what do I get? The absolute value of -1 is 1. The absolute value of -2 is 2. So this is an even function. And then the reciprocal, okay, it looks like it. Looks like something's going on there. Let's check our math. It's definitely not even because I don't flip across the y-axis. So let's check for odd. Does this match up? If I plug in 1, I get 1. If I plug in 2, I get 1/2. What happens when I plug in, oh, when I plug in 1/2, I get 2. So what happens when I plug in -1/2? I should get negative whatever this answer is. Do I? Yeah. What about for the next one? When I plug in -1, do I get back the opposite sign, the same number with opposite sign? Absolutely. When I plug in -2, do I get the same answer but negative? Yep. So this one is an odd function. Wow, that whole word got away from me there. Like, you can save it, you can save it. All right. So that one's an odd function. All right. Let's go back and take a look at the ones we skipped. We said the square root is none. X squared, yes. X cubed, yes. Just any general linear equation is not going to have a general case, is not going to be symmetric, because if I flip this over, it's linear. It cannot land back on itself because it has to be a straight line. If I rotate this around the origin, this line will appear down here, right? And that's not symmetry about the origin. So this one's not going to have any. A constant function is not going to have any unless it is the line, or the line y equals 0, unless it's the x-axis. But my identity function, this is a specific case of linear equations. This does have symmetry, right? It's not about the y-axis, but it is about the origin, right? If I rotate this 180 degrees, what's up here comes down here, what's down here comes up here. Does it match my rules? F at -x is equal to -f at x. 1 and 1, 2 and 2. When I plug in -1, do I flip the sign of the f of the output? Yep. When I plug in -2, do I flip the sign of the output? Yep. So this is an odd function. Okay. Odd and even are very specific terms. They have meaning in math. They're not going to explain all of these, but I want you to look at least these three. What do you notice about the odds and the evens? Anything about those identities or anything about those functions step or jump out to you? So here's the identity function. If you're trying to figure out what are the functions that we're graphing, there they are. Anything about even and odd and about those functions jump out? Yes, it does. Okay. So these are special cases. If you just, if you scoot this parabola over 1 unit, it loses its symmetry. So these are specific cases. But for the specific cases, notice x cubed is an odd function. X to the first is an odd function, right? This is when x is there, but no exponent is written. There's an understood 1 there. Well, the highest power of x, that's odd. This is even, and this one is odd. That is not a coincidence, all right? So the farther we get into this, there's going to be there's going to be another definition of an odd and even function, because we're going to start talking about power, or start talking about the highest power of x. But for this section, if I just have that general x to the just x squared, x cubed, I don't have any other terms with me, the power of the variable is going to match up. If the power of the variable is even, the function is going to be even. If the power of the variable is odd, it's going to be odd. Now, that does not explain the even and odd down here. That is just a feature of the functions where x is an integer, or where the power of x is an integer. Now, down here, there is no really easy, simple way to remember, or to say, oh, well, look, the absolute value is a power. No, you can't do that. And then, so what you have to do for these is you just have to remember your rules. If it's odd, f at negative x has to return negative f at x. If it's even, the rule is f at negative x will return what you started with, f at x. All right, so that's even and odd. Okay, again, last time I'm going to say it, you graphically look at it and you're looking for those two types of symmetry. Algebraically, you look at it as, if I plug in, notice both of these start out by, if I plug in negative x to my function, even is going to return the original function, odd is going to return the negative on the outside. So both of these start with, just plug in negative whatever you're looking at, see if you get the original. So algebraically, identify if these are even, odd, or neither. Okay, it doesn't have to be even or odd. Their functions don't have to be one or the other. It is not a binary choice. So let me show you exactly what I was talking about. Okay, so this is f of x. Okay, and I'm just copying it from here. So I'm going to check, is this even, is this odd, or is this neither? If it's even, I've plugged in negative x, I'm going to get back exactly what I started with. If it's odd, the first term is going to become negative, the second term is going to become positive. And if it's neither, something else happens. All right, so what happens when I plug in negative x? Okay. -2, negative x to the fourth, that's negative x times negative x times negative x times negative x. All the negatives pair off, right? I got negative x times negative x is x squared. Negative x times negative x is x squared. X squared times x squared is x to the fourth. Okay, and then what about this part? The absolute value of negative x. Does the absolute value of negative x give me the same thing as the absolute value of x? If you plug in negative x and then take the absolute value, do you get the same thing as if you plug? It will reverse. Yep. Right. So so what I'm saying here is if here's x, here's the absolute value of x, here's the absolute value of negative x. If I plug in 1, I get back 1, I get back 1. If I plug in 3, absolute value of 3 is 3. Absolute value of negative 3 is 3. If I plug in negative 2, absolute value of negative 2 is 2. Absolute value of negative 2 is 2. So what I'm trying to get at from that is absolute value of negative x is the same thing as the absolute value of x. Yep, they're the same. Now, I can't do any more math here. And notice really quick, I did not factor that out. This did not like go out front or anything. It just, the absolute value of negative x is the same thing as the absolute value of x. Now, what is this? Okay. If my result is f of x, this function's even. If my result is negative f of x, my function is odd. Does this match the original? Okay. Is this the original f of x? Yeah. Yes, it is, right? The signs are the same. Plus 5f. Yeah. So this is the original f of x. So that means this is an even function. Okay. Now this is where you could I could easily see it being confusing, because up until this point I was just saying plug in a negative. If you plug in 1 and you plug in -1, what happens? If you plug in 3, plug in -3, what happens? Now I'm actually plugging in a negative x and seeing what happens. So let's go to the next one. G of x is equal to 4x cubed minus x. Okay. Now I told you that if my that symmetry works if I don't have any coefficients and any terms other than the top one, and my power is odd. Well, this one, the power is odd, but I've got some other stuff going on. So I want to check it. So I'm going to plug in negative x, and what's going to happen? Negative x cubed minus negative x. Negative x cubed is what? Negative x times negative x is x squared. X squared times negative x is negative x cubed. Minus x becomes plus x. And then what happens? So does everyone see how this negative x quantity cubed and negative x cubed are different things? Right? In this case, I have to cube by order of operations. I have to do this cubing first. I've cubed it. Now I have negative x cubed. Well, 4 times negative x cubed is negative 4x cubed. All right. So this is g at negative x. All right. Is this the original g of x? No, it's not. But is this the same thing with all the signs flipped? Yeah. f4x cubed is still my first term. It was positive here. Now it's negative. This was minus x before. Now it's plus x. So this is negative g of x, which means this is an odd function. Does that make sense? Okay. Now, we can extend this a little bit. Remember, I told you it was if that x is sitting there by itself. But in this case, I have x's of that are cubed, and I have an x to the first power. Both of the powers, all of the powers that I encounter in this problem are x to some odd number. So what am I going to end up with? I'm going to end up with an odd function. Why is that? Because when I raise a negative to an odd power, I get this term flip signs. When I raise this, or when I take x to the first and I plug in negative x, what happens? It flips the sign. So that's the idea here. All right. What do you think is going to happen for C? H of x is equal to 2x squared plus x. So I plug in negative x. That's going to be 2 times negative x squared plus negative x. Negative x times x. Negative x times negative x is x squared. Plus negative 2 is just minus x. So this is h at negative x. Does this equal the original? No, it does not, because that sign has flipped, but this one has not. Okay, well, first of all, it doesn't equal the original because this sign has changed, right? So it's not even. Is it odd? Well, if it's odd, both the signs changed. This one changed, yes. This one changed? Nope. So this one is neither. And then let's look at the last one. K of x is equal to x squared minus 3 over x. Anybody got a guess right off the top? What is going to happen here? K at negative x. Neither? All right. Negative x squared minus 3 over negative x. Negative x times negative x is x squared. The minus 3 is not impacted. And now the denominator is negative x. Okay. Is this the original? Nope, because the denominator changed. Is it odd? Did each term change signs? Okay. So let's take a look at what this means. Okay. I'm dividing by negative x now. Does everybody agree? First off, let's come back up here. Is everybody cool that I say x squared minus 3 all divided by x? Will that be the same thing as if I had x squared divided by x minus 3 divided by x, right? Same denominator, I can put them together. So now if I put them together, I can break them apart. Well, this reduces now. X squared divided by x is x. And then 3 over x is just 3 over x. There's nothing to do with that. What happens if I do this same breakup over here? X squared divided by x is x. A positive divided by a negative is negative. So this is negative x minus 3 over negative x. Well, minus 3 over negative x is minus negative. So this becomes a plus. Now look at it. It's not the original, but did all the signs change? X is now negative x. Minus 3 over x is now plus 3 over x. So everything changed. So it turns out, believe it or not, this is an odd function. All right. I debated with trying to tell you about the powers because what's happening here is I end up, this is a, what happened is this is x squared, but it's really x squared divided by x. So I end up with x. This has an odd power, right? We learned from the last page that inverse functions, or my reciprocal, or where x is in the denominator, that 1 over x, that's an odd function too. So what I have is an odd function minus an odd function, and the result of that is another odd function. So sometimes it's not really easy to see when it's written out if we don't take some time and maybe even break the problem down a little bit more. It's really easy to see when I can see each term separated by pluses and minuses, and not where I have a numerator and a denominator both with x in them. All right. So that's increasing, decreasing, and constant. Refresher here on, or sorry, that was even an odd. Here's a quick refresher on increasing, decreasing, constant. Okay. So this graph approximates the altitude of an airplane f of t at a time t minutes after takeoff. All right. So what's happening? When you look at these problems, I want you to, and I really don't know how, because I know I thought about this mentally as I was doing them. This is not the flight plan. The plane, this is not me tracing the flight, the airplane going up and then moving forward and then coming down. This is just me talking about what is the altitude after this many minutes of flight. They look similar, but I don't want you to think that this is a trace out of the plane. This is the plane's altitude moving through time, not the plane moving through space. All right. So what are the intervals where the plane is increasing in altitude, decreasing in altitude, and constant in altitude? All right, increasing. Okay, that's rising from left to right. So all of this up until here, looks like until we reach 29,000 feet. All right, so this is increasing. The next thing I encounter is we fly at 29,000 feet. That's constant. And then just like all things that go up, they must come down. I'm falling, 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 falling. And this is where I decrease. All right. So where am I increasing? Where is my altitude increasing? Okay, well, it's increasing over here. Now, I don't say it's increasing from altitude 0 to altitude 29,000 because there's a couple of places where it is those things, right? It's the plane hits all the values of altitude between 0 and 29,000 over here. It also hits all the values of 0 to 29,000 over here. So I don't talk about where or what are the intervals in terms of y. I do it in terms of x. Or in this problem, this is the t axis, and then this is the f of t axis. So I am increasing when? I'm increasing from, I'm not increasing at takeoff, okay? So I don't include the 0, but I do include everything past that. And then where do I stop increasing? I stop increasing right here, which corresponds to what? Let's click right there and see what we come up with. Looks like 40, right? I know that's just a little bit off. It looks like I'm increasing for the first 40 minutes of the flight. So 0 to 40. And then I stop. Now, notice again, I did not include the endpoint. I did not include the 40. And the reason is, once I hit 40 minutes and I've hit the altitude of 29,000 feet, now my plane's constant. It doesn't rise or fall. So this is the point, 40, comma, 29,000. Okay. So I'm increasing from t is 0 to t is 40. Next, where am I decreasing? Well, let's do the constant next. Where am I constant? I'm constant from 40 minutes, just after 40 minutes of the flight, all the way up until, looks like, wow, that's not even close to where I clicked. Come on, play with me. Maybe there? That's not gonna scoot, is it? No, of course not. Oh, maybe, ooh, maybe. So if I had to ballpark that, let's just do a freehand. Let's see how terrible my freehand is. If I just come down from there, it looks like 120. So is everybody cool if I call this point 120, 29,000? Everybody agree to that? Yeah, okay. So where am I constant? Well, I'm constant for this entire part of the flight. When am I constant? I'm constant from the time, not at 40 minutes, because at 40 minutes is where we went from increasing to constant. So when I hit that 29,000, when I hit that ceiling or I hit that 29,000 feet and I stop rising, at that point, I'm not rising or falling. So I don't start this at 40, I started just to the right of 40. And just to the right of 40 means parentheses 40 all the way up until 120 minutes. And again, I do not include the endpoint. Lastly, where am I decreasing or when am I decreasing? I'm decreasing just to the right of 120 all the way until I land, which I think looks like happens 160 minutes after the flight started. And let me just point out these other 2 points. That's 0, 0. And then this is 160, 0. So there are the points that are interesting to me. Okay. What was the maximum altitude of the plane? What's the highest the plane went? We went up there and cruised. It went 29,000 feet. Everybody go with that. All right, so that's increasing, decreasing, constant. Oh, yes, looks good. Okay. What if I take, let's just skip that. I think we're good. Increasing, decreasing, increasing, constant, and then I decrease. Okay. Let's put it, let's ask you that same question. You know what? Now that I see what it's leading to, we'll do it too. But we'll do it quickly. Okay. Because I want you to notice the relationship that happens next. I am going to assume that these have arrows on the end, meaning the behavior continues. So I'm increasing all the way up this. And then what colors did I use? Decreasing was green. So then I start to decrease until I reach that bottom. And then I start increasing again. And then I go constant for a little while. But as soon as that starts to hook down, now I'm decreasing again. All right. So increasing. All right, well, we're gonna let this be X and F of X. So that way our variable on the X-axis is the letter X. So where am I increasing? Well, let's start on the farthest left and work our way over. I'm increasing from anytime you've got that arrow on the end, and I am increasing from left to right. That means I'm starting out at negative infinity, and then I keep increasing until I hit this point right here. What is this point where I change behavior? To 0, 2, let's see here, -1, -2 is my X, and my Y is 1, 2, 3. All right, so from negative infinity all the way to -2, and then it stops increasing. Endpoints are never included in increasing, decreasing, constant, so you can always put parentheses. Where else am I increasing? Well, it looks like I start again right down here. Good, and then we just got to tie them together. So right here, I pick up increasing again. That point is 0, -1. And then this point is 2, 1, 2, 3. Okay, so I start increasing again at 0, and I do that until I reach 2. To tie together intervals, we need to use the union. So that's what that little U is. That's where I'm increasing. How about decreasing? I am decreasing. I start decreasing at -2, and I do it until I reach 0, parentheses, and then I do it again. Where does it pick up? I'm going to argue, I think the decreasing, I think it starts there. The constant stops and decreasing starts. That point is 4, 3. So I pick up, I went from -2 to 0, and now I'm going from 4 to positive infinity. And then where am I constant? I'm constant from 2 to 4. Okay? How does everybody feel about that? This is from that page 206 in the book too, so if you're looking at the book, absolutely. Okay. Now, notice two things. Interval notation, the left, whatever the number is on the left is always smaller than the number on the right. All right. -2 to 0, 4 to positive infinity, 2 to 4, negative infinity and -2, 0 to 2. And notice my intervals are in order. This negative infinity to -2 is to the left of 0 to. -2 to 0, this little green, the down part of the parabola there is to the left of the other decreasing zone. So order matters here, and notation matters. If you don't put x is an element of or t is an element of out front, this one, you know it's an interval because it's got infinity in it, but that just looks, that's an ordered pair. That looks like a point, that looks like a point, that looks like a point. So interval notation is necessary. Now, I want you to look at that same graph, and I want you to consider something else. We talked about relatives, mins, and maxes before. Again, I'm going to extend these forever, so that way endpoints don't become a problem. Relative maxes and mins. Okay, well, I think I see a relative max right here. And we've already talked about this point. That is -2, 3. So that means I see a relative max, second lowest or highest. We're always going to be talking about relative here. The global, sometimes the global exists, sometimes it doesn't. In this case, it doesn't. There's not a global min or max here because the function is going down forever in both directions, and the highest y value occurs more than once. So we're just talking about relative maxes. So that's a relative max of 3 that happens when x is -2. The other place that you might think is a relative max is right here, but it's not, and it's because this is constant. If there are points that are lows, which would be considered relative, yes, there are. There is a relative min in here too. So this one right here, while you'd be tempted to say it's a relative max, it's not, because at this point it's 3, at this point it's 3, at this point it's 3. There is no interval where I can trap that point and everything else in the interval is below it. I can do that here, right? If I start here and I come to here, every single point every single x value in that interval returns a smaller value of y. Yes, exactly. I'm looking for an exact point. So that one is a relative max. And then, no, not one. A relative min, well, that's the bottom of the parabola here. We've run into this already. This is the point 0, -1. And I would say I have a relative min of -1 when x equals 0. All right. Now, think back to the last page. What's happening leading up to those points? Any pattern that you notice? What's the function's behavior leading up to the relative max and then leaving the relative max? What's the function's behavior leading up to the relative min and then passing the relative min? Anybody notice a pattern here? Linear to something else? Good, yeah. Okay, in this one, it's a linear equation, then it goes to a quadratic, then it goes constant, and then that looks very steep, so probably a higher order polynomial. But it's linear and then it's quadratic. What about its behavior? What is it doing? What is the function doing to the left of the maximum, and then what's it doing to the right of the maximum? Think back to the last page. What am I doing all the way up to here? I'm increasing, right? Yes. So take a look at that. So let's think about this behavior. Function is increasing, or let me say it the other way. When a function changes behavior from increasing to decreasing, the point at which it changes will correspond to a relative maximum, right? Does that make sense? If I'm increasing and then I start to decrease, isn't the point where I'm changing my behavior, isn't that absolutely set and has to be a max? And then take a look at the minimum. And this is a conceptual thing, so it's going to take a minute. So if you don't understand quite what I'm saying, it's going to take a minute. But take a look what happens here. Increasing to decreasing. And then what happens when I run into that relative min? I go from decreasing to increasing. So all the same words. When a function changes behavior from decreasing to increasing, I gotta fix my grammar up here. The point at which it changes will correspond to a relative min minimum. What do you think about that? So you can see that they influence each other, right? If you change your behavior from increasing to decreasing, you're going to naturally leave a relative max. If you change your behavior from decreasing to increasing, you're gonna naturally leave a relative min. What happened here in these changes? I went from increasing to constant, and then I went from constant to decreasing. There's nothing special about that. When I stop increasing, if I just go constant, I didn't leave a maximum. If I changed from constant to decreasing, I didn't leave a maximum or a minimum. I didn't leave anything because all the points around it are. So remember that intervals talk that I said earlier? This is where it really comes into play. So a relative max by definition means I can put an interval around that maximum, and every single point in that interval is going to return a smaller output or smaller f value than the relative max itself. I don't really know what letter that looks like, but it's not an X. Okay, what about a relative min? Again, I can put an interval around it, and all the other points, all the other values of X in that interval will return values of f of X that are larger than the relative min. So that's the idea here. All right. So let's put it all together on one page. Ooh, we got 4 minutes. Where am I increasing? Where am I decreasing? Where am I constant? Where do I have relative max? Where do I have a relative min? Okay, let's see if we can do this one quickly. I'm increasing where? I'm going to start from the left and just go ahead and go to the right. Looks like I'm constant, and then I'm decreasing right here. Looks like some increasing. So that's -3, that's -2, that's -1. I am increasing from -3 to -2. I decrease, and then I start increasing again. Yes. And then I pick up here at the bottom, so -1, and it goes on forever. All right. I am decreasing. It looks like that starts at -8 and goes until -3. And I do it again right here from -2 to -1. And then I'm constant just at the beginning. Negative infinity up to -8. Relative max. Relative max is going to occur when I go from increasing to decreasing. Do I do that? Yeah, increasing to decreasing. I only do it once. So that means relative max is 3 when X equals -2. And then relative min, I do that twice. I go from decreasing to increasing twice. So I have 2 of these, and they are what? 2 when X is -3. And I have another one of the same value when X is -1. That is absolutely fine. In terms of a global minimum, it doesn't have one because there's multiple points. There's multiple places where I get all the way down to 2. And in terms of global max, it doesn't have one because my function goes off to infinity. So that is everything together. The last 2 pages, I'm going to post these notes. I'm going to let you do the last 2 pages. We'll talk about them on Thursday. And then this is just more definitions, kind of laying everything out. So this is where we'll call it a day. If you have questions, let me know. Make sure 1-6 gets done tonight. If you have anything else, like I said, let me know. Stick around. I'll hang out for a few minutes. And if nothing else, I'll see you on Thursday.